Our next talk is by Professor Karl Kainer. Karl is professor at Hamburg University of Technology and formerly director of the Institute of Materials Research and head of the Magnesium Innovation Center at Gateshacht, close to Hamburg. He is a worldwide renowned Mr. Magnesium, a leading authority of a highly interesting but difficult material. Kainer will tell us about the status of global magnesium research. Do magnesium alloys have a future as structural materials?
Thank you, Professor. Yeah, good morning. Now coming to a very light material, but a tough material. And to sum up my presentation, to save time, is yes, there is a future, but now we start to see what I would like to present. This is a very nice slide. I used several times. I believe you know everything on this slide. And in the past, I had here saving fuel, 0.5 liters per 100 kilometers. Now we have to switch over to extension of the cruising rate. And magnesium can contribute. And the issue we have to face, we have now to deal with new vehicle concepts. Compared in the past, it was very simple, light, combustion engine, you can save energy if you have a light material, and so on. But now we have other issues, and these are the heavy loads with the batteries and safety issues, and also end of life, which is very important. I will come very shortly on this end of life of magnesium, which is a little bit difficult compared to others. In aerospace application is more simple. You have to have higher payload, and you have to reduce the weight. But for magnesium in the aerospace industry, it's a little bit different as a structural material. But in the end, we have flammability. These are the main issue. Or by the side, also the corrosion properties is also a big issue. Okay, the need for high specific strength material is good. Magnesium has low density. It works very well if you calculate it, but the two is a little bit different. Okay, first, carbon footprint, green magnesium. If you want to do something today with magnesium, the people ask you, how green is your magnesium? And this is a slide, it's from 2018, showing the different processes and different contributions to CO2 in the environment during use and during production. And this is the average pitching process, which is still existing in China. It's about 95% of the process, material processed in this technology, a bit better than in the past. If you calculate some credits, means you use the waste material for concrete and other things, you get benefit. And you get a break-even point in a lifetime of 200,000 kilometers. But we are dealing now with new vehicle concepts. This means finally we have a lower lifetime. And the break-even point is then very difficult to achieve. And you need new processes. New processes, in this case, in this example, here, the electrolysis in the industry in Qinghai, in the desert in China, they bought it from the hydro in Canada and converted it into a technology which is more green. It's not running now really good, but this is the only technology which now gets a solution for the green environment. And normally I have also to add here information about recycling. Because, as I mentioned yesterday, presentation recycling is very important. But not in the case of magnesium. We have a very nice in-house recycling market, but we have no end-of-life market. All the material is going to China, America, and the aluminium industry as a scrap or steel industry, and it's like downcycling for me. It's not one by one back into the alloy development. And this makes calculation a little bit more difficult if you want to calculate a green magnesium. Okay, the other thing is, I like this slide because it's when I started with my Magnesium Innovation Center, it was very low consumption of magnesium, and that was a forecast. It showed these. Everybody said, okay, we have to invest. Yeah, and that is the truth. There's nothing happened. I like those forecasts made by those people. We are now about 1 million tons, and this is for the average for the last 10 years. It's not plus minus something, not more. And one of the reasons, I'll show you one example. I choose here the Chinese price, magnesium, and it happened here during COVID. The price jumped up. We had the same 2008 and everything which was calculated for a new project was stopped. And then it took another 5 years to go up in the development, and the same happened now. The price jumped up because energy crisis and so on. The industry is not really rely in the magnesium market, because this can happen suddenly again. And I can tell you today we have issues with companies like US Mac. You know, Dead Sea is one thing, but Salt Lake City has no water. And now they're thinking about pumping water into the Salt Lake City to get enough brine for the production. They shut down. Again, now it's America depending on, not on China, Canada is also delivering some things. And this will also have an effect on price. Reliability of the magnesium market is lost. Okay, we're coming now for Europe. We are now in Europe. And if you look to this sketch, and this is from 2018-19, this is now 190,000 kilotons magnesium in use. You have here metal, pure metal imports, then alloy imports, powder, and then also in aluminium alloys, and then in products, it's also in the market. This is a total thing. But you don't see any recycling material in this case, because it's not there. It's gone, it's lost. And we are dealing with this, and the main components are magnesium casting and aluminium alloying, and this controls the price. If the aluminium industry is doing well, magnesium price jumped up, and I don't believe they're doing very well. And the other products is not so important. Okay, in this case we need 100% of magnesium alloys. In this case only 0.1% for the aluminium industry. It's a little bit different, and this is more critical for the price. Okay, coming to the processes, I believe this is all well-known stuff. Most of the alloys are casted. We have a very small market, the water alloys, and we have new processes. And see, it's near to zero compared to the other. But high-pressure die casting is a dominant technology. We have also some so-called modern type of technology. And this is here coming back. Thick film molding is a process which is now coming back, especially for e-bikes and scooter, and so for smaller parts. Also, they're dealing with bigger parts probably. Okay, research a little bit different. Only very few research were done in the cast alloy, mainly in wrought alloys. And if you compare to this one here, it's strange. Everybody will now want to work on biomaterial and on additive manufacturing, powder metallurgy. No industry, by the way. In wrought alloys in Europe, we have very limited numbers of industry, I believe 2. You are going to China, you have 100. It's totally different. And there is a market for wrought alloys. But we have to mainly deal with this one if you want to answer the question, is there a future for structural material? It's only a future today in the high-pressure die casting from my point of view. Okay, these are the alloys, well known. But if you look to these alloys, there was a slide last day, which were dealing with the high number of aluminium alloys, 40 and 3,000 grades in steel. Magnesium, we have only 30, about this. And real, we are dealing with 2 systems. The rest are systems used for special application. And then we have some material here for defense and aerospace, racing, sports. Is also a niche market, but value chain, high cost and high prices guarantee. But if you look to these red, these development all took place in the last years, and we're dealing with powertrain application, means for high temperature application. 90% of the research on alloy development was done in this phase. But if you are looking to the future of the combustion engine, do we need those things? I say we have enough. And I don't believe we need more new material which is not going into market. There are other development here, which is very important for the public transport, for aerospace, for for jets, is material which show low flammability. And these are the technologies which is now adopted from different places, and it works very well. But you have to bring it into the process, because if you want to cast those material by high-pressure die cast, it's a little bit more difficult compared to the other technology. Yeah, this is a thing which we're dealing. People like to add some of this alloying element, become good results, and the result is mainly increasing the cost. And the castability is reduced, and then you have issues, and the people can't handle it, and the mechanical engineer can't design a new part from this data they got, and it ends with stopping of those activities. And if you look to those alloys were developed in the last 10 years here, they are niche market development for Porsche and for racing cars and other things. Nobody really want to sell it, and especially if you are dealing with a combustion engine free e-cars, there is not a need of those materials. But there were very few development in the case of crash versions. Very few, nothing, near nothing. By an accident, you get a result, for example, rare earths containing alloys showing better crash versions than the other alloys. But it's not good enough. And I believe this is a thing we have to do in the future. If we want to use it as a structural material, we need better results in the crash version, in the ductility and the fatigue. And this is very important. Yeah, take a look at the structure. I believe this is the past. All these very nice big piles with creep-resistant alloys. We have few applications, niche cars. But I don't believe that it will be the future. This is the existing now, and the only part which has really guaranteed survival is the steering wheel. I believe 90% of the cars, the steering wheel, this will exist in future too. But I believe here there are some parts, seats, and we will see if it has a future. And it's a question of market cost and supply. Okay. This is now the idea, and go through now through some of these things. I believe these are well-known parts. These cross-car beams, IPs, bigger cars. This is from the Smart. This is from the S-Class. And this is very strange. This is a part from China, from the truck, and this is cast in one piece. And this is unbelievable. I saw this part. Half of the room, I believe. It's very nice to see that they are able to do it. I don't know about the performance, but it looks good. This is one thing. Then we got going to the e-cars, electric vehicles, and we have now the chance to use those materials which are well known, AZ91, for different types of application, housing, transmission, integration, side cover of motor, side plates. And these are examples. These are the weight of the different type of parts. And I have to learn that also some of those parts are running at higher temperature. And then you have to deal not with AZ91. You go back to those alloys which are more creep resistant. And this is more complex. But I believe there we will have a future. But I don't believe that we have to develop a new alloy for those applications. The existing alloys will doing the job in the future too. Yeah, one example here, which is housing the drive module. Sorry, I was too fast. The drive module. And this is also a very nice part because it's giving a certain weight reduction and also some weight for the magnesium market. And if you have a large number of those things, you can overcome the issues of a market. And there's another thing, and there was a discussion yesterday. This is a Tesla, and you have here the magnesium giga casting. And it was already cast in magnesium as an example. It was shown it's possible, but it substitute one by one. I mean, it's not redesigned to magnesium, only using the same die and cast. And you look to the size of the machine, we are dealing with more than 8,000 tons. I don't believe in Europe we have many of those. We have those in China. I saw those things, and I saw also the part. I was really impressed. It's possible, but I don't know if it's advanced enough in the development. There are some other problems they have to face in the application. And this is another thing which is very exciting: battery upper casting, and this is also cast already in different companies to test if it's possible. And this is possible to cast. Now, in this case, we have to deal with other problems. Environment problem means surface treatment. What is about crash relevance? What is about the corrosion resistance? And also what happens if it's heated up? It's a little bit different, but it is possible for the cast point of view to do it a job. Yeah, that was a very short excursion in this market. Now we're coming to the thing which is I believe for me, normally nonsense. You start with the ingot, you convert it into powder by grinding or by atomization, and then put it again into technology, produce a single part. But I have to learn that it is a green factory, because you can build it in one day without any issues. If you're working with a casting equipment, melting furnace, you have environment issues, you have to fulfill requirements for fire and so on. And this is making things more simple. You have a large possibility of variation in the granules. You can mix it, you can make MMCs, you can do everything with it. A very good technology, a little bit more costly, but it works, and I believe people know how it works, like a polymer extrusion system, a higher temperature in this area, and then you get a shot, which is then near the side. In the past, people like to use this technology to do die casting. They heat it up at temperature where the material was molten. Better is to use a semi-solid technology for this market, for this application, and they now try to do it. You see here are some of the examples. It's running. It's a German company, very nice name. They're doing the job for these e-bikes. And this is another example, and you see why it now becomes more interest. You see it's a seat part, and what you can see here is a sprue and the runner. This is the only part which is waste. And this is still a bit different. In the past, you have 40% of waste. First, you convert it into powder, and they have 40% of this expensive thing. Now we have only 2 to 5% less than in some of these magnesium castings. Okay. Seat structures are also showing up. This is stick to molding. This is high pressure die casting. This is also something which will have a future. Even there are some issues, but also in the public transport for buses, trains, and other things, there is also a future, but you have to use a different alloy. This is, by the way, the problem. Or you have here some housings. The number of small housing produced by thick to molding, and this is also showing good performance, and also the cost is okay from this point of view. This is very interesting. It's a battery housing for a new different system, not for the car. And this is aluminium extrusion and overcast by Tixo-molding with some magnesium alloys. And this is a net-shaped technology. You use the extrusion, then you have the overcast, and then cut the runner, and then you have your part. This is existing, and it works very well in those applications. Okay, this is I have to show it because the competitors of the research they did here is steel, and I was involved in the development of this alloy, and there's running. I don't know if Husqvarna did a job and running now, but this is running for 2 years. This is a piston. It's also a creep-resistant alloy, the application. The mass production, more pistons than engines in automotive, but the weight is a little bit low. It means you're dealing with 100 grams is nothing, but it's a very good market, and it shows that it's possible to produce creep-resistant alloy for a motor application. Okay, this is another thing which is very, very common. E-scooter, those parts are high-pressure die cast and then put together with the motor, and you have different type of application. It works also very well, and also from the cost side is doing well. We have some companies in Europe who do this job, but very few. It is a niche market in Europe, but it's not a niche market in Asia. They produce megatons of those wheels, and on the very low cost side. Yeah, this is the only slide I would show you the sheet development. There was also about 10 years of research on the development of technology and alloys for new sheets. By the way, I'm a little bit sad because we have no industry in Europe who use it. You have to go to China. In China, you have 3 companies done this technology, twin roll casting, and then this rolling. You get this very fine microstructure. You get the texture you need to have better deformability in the processing. Hemming is possible, and this all thing is so fine. There was a solution for the coating, everything fine, but nobody want to pay. It's too expensive, still too expensive, and it was run in a Porsche application. You had, I believe, 130 pieces a year, roof part and GTR3. But the market is not really developed in Europe. In China, you have a number of applications, buses and trucks. You have also in concepts for the high-speed train. They're a little more risky doing those things like the European. They're more conservative in using magnesium technology. This is the only one to show. Normally, it takes me 2 days to explain how important it is. But today, I have to say the future is not really clear. Yeah, flammability. This is a very nice slide for magnesium electron. By nature, those alloys which magnesium electron delivers are non-flammable alloys because a high amount of rare earths, but nobody can pay. It's very expensive. You are dealing with 120 to 200 euro per kilogram of those alloys, and it's only for aerospace and defense. And they have found a market. Since we have some issues from February last year, we have a better market now for those things too, unfortunately. And there is a technology developed in Korea, simple adding calcium oxide, and the material shows limited flammability. But you can also convert it without calcium oxide. You can work also with calcium or ether. And this is the same. The mechanism is not the oxide. The mechanism is the calcium which oxide on the surface, and then you have protection. This is doesn't matter what you use. And this show here the possibility for each of those alloys which are existing, AZ91, AZ31, AM50, you can add and it works. But the castability is a little bit more complex. But it's very good, it's work. And those are some examples. It's a German company, not is it from Austria. They bought the license from the Korean and now make trials with other industry to develop seats for the aerospace application for civil aircraft. And this is doing well, and you can use it for all technology which are available. Extrusion, textile molding, casting, it's good, and recycling is not the issue. Yeah, the other thing is additive manufacturing. Everybody is doing also this job. This is, in the case for magnesium, a little bit different. It's mainly for smaller parts. As you have these technology like laser powder bed fusion, or this wire. This is for bigger parts, and this is, for example, for bio parts, for implants. This is technology which is used for some of these applications. And very exciting is you can create a patient-specific implant with this technology. But it's also a little bit more expensive, but it works for this case. And these are some examples to show the possibility of the additive manufacturing. This is totally different to aluminium and other material. You can't produce parts like they did, spare parts and other things in this technology. In magnesium, it's a little more difficult because the cast properties are a little bit more different to the properties. But if you look here to this example, this is possible, and they are doing a lot of trials. And this is the biomaterial. This is a big market in research. In Germany, we start with 3 groups. Now we have 200, I believe. And everybody uses AZ91. It is a mistake. But it shows here the row. You start with the ingot. You convert it into extrusion billets. The extruded material, you drill a hole, and you make a tube, and then you make a stent from it. If you have some heart attack issues, probably this is a solution. Thank you. I show you here some of those examples, which is existing, and there are German companies here, and this is an Aachen company. It's a spin-off of the university. And they are on the market. There was this trouble, but they have on the market. Approval is a big issue in this market. Okay, corrosion. This is one thing I want to show. Normally, I need more than 1 day. If you have this new application, you need a specific corrosion protection concept. And you normally start here with the high purity. It's done 60 years ago. And now adding some elements like calcium and rare earth, giving better corrosion resistance. This is one thing. But you have better to modify the surface, conversion coating, and then you start with a different coating. In the end of the day, you end with a perfect coating system, and this means today it's possible to develop systems which are self-healing. And this is, I believe, a most important thing. The issue finally is the temperature stability of the coating if you are dealing with parts, battery, which can heat up or other things. This has to be developed in the future. Now coming to, I hope the conclusion. I put it very rough. Normally, if I read it down, the presentation was done. But I would like to focus on, this is a market issue. If you want to have future, you have to stabilize the market. These automotive industry have to reorganize the discussion on the use of magnesium. You need public transport. You need mainly non-primary alloys. This is also in mass production. Biomaterial, you have large activities, high value added. It doesn't matter what it costs. The material is not a big price. The process is more critical, and the approval costs you 1,000% of the price of the material. Aerospace, I mentioned, and this is also a big market. It's coming up more and more small parts, but it's not the mass production in kilograms. And coating protection is very important. And if you look to this, a presentation about application in China, again, took you a day. Because they have many advanced technology, and they are dealing with consumption of magnesium of 600,000 tons compared to 190,000 tons in Europe. Thank you very much.
Thank you, Karl, for the interesting talk and the interesting material.
Yeah. Karl, thank you for the talk. In China, where there's a lot more activity, is the magnesium being recycled at the end of life? Is there a process? Is there a loop? Or not so much yet?
No. This is the same issue. You know, everything which is dealing with in-house, this is no problem. End of life, you have to separate the material. Normally, it's more easy to produce a type of lightweight material fraction. And this you can put into the aluminium. And there's less copper, they can work with this. And this is the same issue we have to face. They also buy scrap from Europe and taking the scrap also for the steel and also for the aluminium industry. They have no system to collect those materials. Right? This is a little bit different. In the past, they have groups who were able to separate aluminium from magnesium by hand. Yeah, that's experience. Smelling is right. If you have ammonia you smell, you know this is magnesium. And the Indians also do it by hand. And then you have magnesium fraction. They have good results, but it is tons, but not megatons. Yeah. Okay.
It's not a scientific question, but I'm not sure if I saw the numbers correctly. During COVID, you said the price went quadrupled?
You know, it's 22. You know, the problem was...
What was it? Was there a demand?
Energy.
Oh.
Energy. There are problems with the energy costs in China at this time. It's not dealing with the war. It's not dealing with the COVID. A little bit with the COVID. But they have a gap, energy gap. And this immediately jumped up the price. They need, normally for the reduction, natural gas today. In the past, they used coal. But now natural gas is a little bit cleaner, and there was a lack of natural gas in this time.
We have another question.
I can't believe that stents are made out of magnesium alloys. They're far too reactive.
You have to test it.
In the UK, they're made out of platinum, for God's sake.
By the way, the company who produces those stents, looks for magnesium electron. Do you know they have their own small plant to extrude the material in high quality and drill in the holes and deliver it to the Biotronic company, and those stents are then laser cutted and polished, and they're running. You can drink and smoke, and you get a result after 2 days. Yeah, it's not a joke. We have a large number of industry also in China doing it, and there's a big market. It was also developed for kids. I learned about this.
It's actually being implanted because it's a very reactive material to be putting in.
Yeah, this is the reason. They are gone. This 360L is stable. This is stainless steel over life. But this disappeared about 6 weeks, 8 weeks, 2 months, and this is degradable magnesium. But the issue in this case is control corrosion. If you have a fast control, you get all bubbles. With hydrogen, but it's really true, and the material they use is WE43 because this is a material which corrodes slowly and accurate. Hopefully.
Okay. I think we stop here. Thank you very much.